Can't all be zingers. That's what you get. All right, yeah. So, section 1.1 continued because I'm doing it however I want from now on, which I quite like. I'll write it down in a second, copy. Plus, with the magic of editing, none of this will be in there. If you're live with a student or on Twitch, you just got to suffer through that like Lorenzo does. And so this is how I do it. If you're taking a class from me, you'll be like, yeah, that's how that happens. I'm early, prepping, filling the board with freaking knowledge. Mark's always 10 minutes late and just spits out more than me in fucking 30 minutes anyways. But I have to get there early. So I'll be there early. I got it ready. But then it takes a while for me to draw it out. I'm not bringing notes. I'm not referencing anything. I've looked at and started writing the Math 114 and 115, which they call that, which I'm going to call Calculus 1 from now on. And what we have to do and segue from last time was we were doing notation, notation, notation. I want the copy, paste, copy, paste, copy, paste, but those are fairly 3 consistent notations I drew in a row, which is why we need good notation, including your cursive English sentences. Oh, sadness. So once we do that, what I did last time when I finished off was I listed a bunch of sets of numbers and I cheated and I said what the types of numbers were, and then I said that the real numbers are essentially going to be the disjoint union of the rational numbers and the irrational numbers. So I can break it into 2 types. How is the easiest way to see that? Using the green pill. Start growing things intellectually and out in your garden. Stop taking red pills, blue pills, black pills. Take the green pill with us, and yeah, it's gonna. Oh, that's the guy I have to stare at. I like ocelots. I like turtles. I like ocelots. Oh, I just gave you 2 sound bites. Damn it. Why would you say that on camera? Sometimes Jay says stuff. Okay, so where was I? I cheated and said that the real numbers are going to be the disjoint union of the rationals and the irrationals. So I can break what we call the real numbers into 2 types of numbers. Using the green pill, what that is going to essentially mean is theorem. Every number can have a unique decimal expansion. And that decimal expansion either repeats or doesn't repeat. If it repeats, you're a rational number. I think it was over here last time. It doesn't matter in my mind. If you're a rational number, unions are commutative. We'll do that. No, we won't. You're either a rational number, which means you have an infinite repeating decimal expansion, or you're irrational and you have an infinite non-repeating expansion like pi or the square root of 2, which we can show. Once we have the real numbers, then what we're going to do is in the later chapters, we're going to chapters, I don't know what they're going to be, YouTube videos. In the next section, we're going to do functions of real numbers. So then we'll study all the properties of functions and what are the main properties of functions. What we're going to want to do is we're going to want to talk about domain and range of functions, graph of functions, one-to-one functions, and onto. And the thing that they suppress in a lot of the books when they do the calculus and not the calculus of variation is the average rate of change in an interval. The average rate of change, the limit of an average rate of change is going to be instantaneous rate of change, which we're going to call derivative of a function at a point. That'll be the next idea. That's unfortunately the easy part. Then we're going to do the other direction. You're going the wrong way. We're going to do antiderivatives, and then the course usually ends there. We're going to keep going and then expand into, once we have the antiderivative and then the fundamental theorem of calculus and Riemann sums, we will give you a bunch of techniques of integration and applications of this as well. This is where we're going. Let's go. What we're going to start off with is notation, notation, notation. Should I do that when I'm not wiping? What we're going to do is, now that we have this, we'll start off with notation, and then I'm going to use the notation specifically to intuitively describe, using the green pill, what a real number is. So ask yourself this first, is what I usually pose. There's the symbol I'm going to use. This is a set. It's got all the real numbers in it. Can you describe this in your own words? Yeah, it's a trick question. Neither can I. Take the red pill with Sean and then he'll show you. It's unique, whatever it is. Let's go. So, definition. Also in there, eventually on Twitch, etc., you have to shout it out, but you can't shout through the TV screen. But if you don't recognize a notation, in the comments, comment something and I'll tell you what that symbol was or what I meant when I do this, implies. That's definition. The tick is, yeah, the abbreviation. I'm lazy. Definition. A set I can't red pen, black pen. A set is a collection. I don't know if I spelled naively right. Naively is a collection of objects. The axiom of schema of comprehension actually says that if anything has a property, there's a set with that has all those things in it. You can make sets of things, which we're going to do with numbers, baskets. And these objects are called, how would come here? An O. I don't like you either. Edit that. Are called elements or members of the set. And then so once I have the definition, you should ask yourself in there, usually they say denoted by respectively, and then we'll just do notation. All three at once. A, B, C, etc. X, Y, Z, lowercase are going to be elements. And uppercase, capital letters are S set starts with S. So that's going to happen a lot, are the sets. And now I magically erase this. Once we have what the little guys are called, and a notation for the little guys, and a notation for the big guys, we want to say, we want to reference in a lazy way, these guys are inside these guys. So how do I do that? I should just do a whole bunch of those. And then you can, it's like, I should just do a bunch of those in a row with this shirt on. There you go, you're welcome. So this is our definition. Once we have the notation for elements and the notation for sets, what we want to say is, let's use this. So what is this going to be read as? This is a sentence. This says little a is an element of set A. And then how do you say not equals? The same way you say not in. So X is not in. X is another way of saying that. So this means in or element of. And this is the negation of that. We'll get into that sentential logic in a bit. Easy, baby steps. So this is our first notation. Then what we want to do is, just like we're going to start the first, I'll start the notation for what the natural numbers are, then I'll have that, and then what I'm going to want to ask is which numbers are in there, which numbers are not in there. We've already cheated because I haven't even developed them yet, but you already know some of the numbers like 0, etc. won't be in the positive integers. And then what we want to start doing is, once we have those elements, we can start talking about operations, binary operations, and binary relations. We'll start with binary operations because I want to create in the set of positive integers, or the natural numbers, I'll call it, Sean. In the set of positive integers, I can now, with that operation, I can take two elements and make a new one who may possibly be in there or not be in there. So if I take 1 plus 2, that's going to create the new guy 3. In fact, what you use as the generator in the P&O axiom is 1, and then 1 plus himself gives you the predecessor, 2, successor, other direct. You're going the wrong way. Successor. I'll get them straight. I have this mild dyslexia, which flips things when I do numbers too. You'll see. So once I have that, I can add numbers or combine them to create new things. Sets are bigger objects than the elements inside them, so we're going to have more than one way of combining using union, cup, and cap in latex. Union and intersection, which is or and. Union will in general create a bigger set if they're not equal to each other, and intersection will in general create a smaller set if they're not, the two original sets are not equal. So we're going to remind you how to combine using the binary operation of plus and subtraction at first, how to combine positive integers, and then immediately I will give you the definitions for how we combine sets. So the first thing that we're going to do is definition. We're going to define the set of natural numbers. The set of natural numbers, which we're going to underline as our definition, is given by rote. So how do you make this fancy n? First of all, they never show you this either, so I will. Draw half of the n, and then draw the other half slightly down. And then a z is going to be an n rotated 90 degrees. We'll get there in a second. He's next. So what is this guy? How do we draw that again? Like this. And he's going to be equal to, and then I'll give you the bracket by rote also. Right now this just means it's the basket that the sets are in. That means that anything in there is what I'm calling that set. 1, 2, 3, 4, 5, 6, 7, 8, 9. I can put 10 so that you see all the Hindu Arabic symbols. So for now, even here, we're cheating. The ellipsis means that I go forever, and then the numbers don't stop. And this is the Archimedean principle. The integers and therefore the real numbers have no upper bound. Think of the largest number, infinity is larger. That's where we cap it eventually. So this is the set of natural numbers. There's the basket. What we're going to have to start doing is start combining. So when we have elements in there, 1 is in n, we're going to say, but this guy, who's one group of 10 and no ones, 0 is not an element of n according to the internet and Sean. I wanted to be in there axiomatically. It doesn't matter. 6, 1, half a dozen out of the other. There's a unique field which is going to do it eventually. So this is what we mean by lazy notation. This just says read as 1 is a natural number and 0 is not. Just in case someone wants to dispute me, that'll be a non-disputable conversation. 1 is in the natural numbers and -1 is not in the natural numbers. That's how we're going to read that. What does the negative mean? It's a sex myth. Opposites attract, likes repel. Ooh, how dare you say that? It's for quantum mechanics and physics, and what it really means is you're going to combine them, and that's what I want to talk about. Once you have a nothing, you have an opposite guy, which we're going to get integers to combine. We don't have him yet, pretend. And so what am I going to do next? Using that, we can do addition. So I'm not going to explain that. It'll be in the lecture notes, which are pinned below. But 1 plus 2 now equals 3. I'm assuming you've done this in grade school at some point, please. Or stop watching the videos. We're going to have to do things you should already know. But this creates a new guy. I'll steal Stuart Calculus from old, but not the functions. But this is what we're doing. The binary operations of plus, subtraction, multiplication, division, nth root are what we're going to do for functions, new functions from old functions, and then composition, which they should call the composition rule, not the chain rule. I'll get there later. But we're creating new numbers from the elements in there. We're creating a new number from the old numbers. What that also shows is something we're going to call closure. When I add 2 positive integers, all I get is another positive integer. It's always in there, so they're in there again. If you do subtraction, 1 minus 2 is -1, which is no longer in there. So subtraction is not closed under, or the set n is not closed under the binary operation minus. Why did I talk about that? Because I now want to take different sets and talk about combining and creating a new set. So I'm going to need the empty set. You'll see why in a second. Definition. Let S because set starts with S, and T because it's the next letter in the alphabet, B sets. Then, so I need those guys for the kind of things I'm going to do. We have, they'll say, oh they. One, which has, you're like, why did you talk about those? Just a second, there's going to be more. I started indexing with Roman numerals, the only thing they're good for, and clocks. The empty set, it denoted by 0 with a line through it. We went over this last time, the subtle details, but that's what I'm calling an empty set. It's my channel. I'm the wizard. That's the empty set. I have spoken. Is the set with no elements. So remark, why did I do this? The empty set can be proven to be unique. So we have to have an axiom that there is an empty set, a void, a nothingness. But luckily there's only one. There's no more than one void. Stare into it too long, it'll stare back, but there's only one of them. All right, so I need that. Why do I need that? Because we're going to try and say, what do two sets have in common? We're going to call that intersection. What if they don't have anything in common? Did we make a set? Yeah, this guy is who we made. 2, that's 3 though. The union of two sets, S and T, that are already given, is the new set denoted S cup T, or S union T, or is what it is. Containing all elements in S or in T. And so that's where we're getting the or from. And then 3, I can squish it in, move Mario. It's Luigi. Do I have to sound Italian every time I say Luigi? Yes, up and down. Luigi, get the fuck out of the way. The cameraman laughed, so I'm good. Now I forgot what I was doing, being a smartass. The last guy, we're going to use this. So the intersection of S and T, it'll be an and, but that's not where that's not the right and, is the set, new set, containing all elements in both S and T. And it's denoted by, I ran out of real estate, so it's my show. This is where I was going. We're going to denote it S cap T, or S intersection T. I'm going to draw a Venn diagram in a second, so it won't really matter. But these are the 3 operations I have, and then I need one more. I lied, I need 2 more. 4. If 5, now I forget which ones. Rein it in, rein it in. If S intersect T is the empty set, i.e. they have no elements in common, then S and T are called disjoint. Disjoint, right here. 5. If all elements of S are elements of T, I'm going to start giving you pseudo sentential logic, like pseudocode. Sentence pseudocode will eventually get sentential logic specifically. Actually, that's it. That's the declarative statement. But then S is a subset of T, denoted S sideways, or possibly equal to T. And then what's the last thing I need? They didn't even give it a name, the irrational's I, so they just called it the reference of the complement of the rationals inside the real, so I have to do a complement. 6, if is, yes, they will be, if S and T are both subsets of some universe of discourse X, then the do I need T? I'm winging it. Leave that in. We're leaving that in. If S, that's how math is done. It's not surgical. We've got to start leaving those ones in there too. So if S is a subset of, I'm going to use T then the complement of S in T, denoted SC, is, what is it, Lorenzo? Elements in T but not in S. Then as I ran out of real estate, but similar to that one, if we write that what S complement means that if X is in T and X is not in S, implies X is in S complement. Let's clean the board. All right, example, let S be, and then that's why next time what we're going to get is set builder notation, and I'll do a bigger example of this stuff too to remind you of what this combining is. But the other thing we're going to need as is instead, what if I said that S was going to be the first 24 numbers? I don't want to write those out, so I want a set builder notation that will tell you it's the first 2024 integers, but I don't have to write them all out. For now, I'll write it this way because there's only 7 of them and 3 guys. This is the first 7 positive or natural numbers. This is the first 3 prime numbers inside the natural numbers. If you can find out where the rest of them are, you can have $1 million plus the juice. 1, find S union T. 2, S intersect T. And 3, T complement in S. Yes, I permuted it. Don't fixate on what I'm calling the things. The rule is what you need to fixate on, what the intersection is. That was an accident, but I'm going to take it. You just saw in real time, I pretended like that was planned, and then I was like, okay, that wasn't planned. But that's how you fucking become a wizard. I don't know what I'm talking about at all. I just make it look like that. So let's be lazy. Equals, not even switching colors anymore. What is this? Run through the definition. I just erased it, but I've got it in my mind palace. S union is everything that's in here or in here. And also this is going to show us a story that we're going to get into. Do you see what's going to happen to it? When one guy's inside another guy, the union will be the bigger one. Yeah, I know. I heard it when I said it. When one set is inside another set, the union will be the bigger set, and the intersection will be the smaller set. So I don't want to talk about that right now, even though I just did. He's editing it all. There. Example. It's just, he's like, I'm putting that on my channel. Example. Let S be the first 7 integers, and let T be the first 5 primes inside the natural numbers. And what we're going to do is find the union and intersection of these guys, and then we're out. So if I have union, let's recall what that is. We just had the definition, I just erased it. So union said it was or, and it means it can be in here or there. So first, the easiest way to do this, especially when it's discrete or just a finite list of numbers, I can write this as 1, 2, 3, 4, 5, 6, 7. It has to be everything in S. And now I say or. Was this in there? Yeah. Was this in there? Yeah. This will be useful for the next thing. Was this in there? Yes. Was this in there? Yes. Was this? No. So there's the union. Anything that was in S or in T, you don't have to write them twice. We'll get into that, but yeah, that would mean there's more things in there. But once he's in there, he can't be in there more than once. And notice that created a slightly bigger object. This is a Venn diagram. So where they're overlapping, this is the blastula is the union. The intersection, that's why the picture is why they're going to call it intersection. This crescent is going to be, that's a convex set. Yeah, it's convex. Why is that convex? Is the intersection overlapping area of 2 circles a convex set? Is any line in between 2 completely contained in there? I believe so. We'll prove it later in just a second. That wasn't what I was talking about. So the outside, so first of all, the intersection, this guy is going to be in here in the picture, and then the union will be everything, the overlap. Sorry, I said that wrong. Blah, blah, blah. I'll draw the Venn diagram in a second. So what is the intersection now? The intersection is going to be anything only in S and in T. So the things I've underlined in purple, that's going to be 2 was in both, 3 was in both, 1, 4, 6 are not in this one, and 11 is not in this one, so I can't use them. 5 is in both, and 7 is in both. And notice that created a smaller set. And then now let me redraw that Venn diagram. If I call that S, and I call this T, and they're inside some bigger set, for now we can call that N. This is T. So what was their overlap? Their overlap was, intersection was this guy, which is going to be 2, 3, 5, 7. Get in there. And then what was the things that were in T that are not in S? 11. And then what were the things that were in S and not in T? 1, 4, 6. This is what we're doing. So the union was, which one can I use? The union was the whole blastula. Everything in either of them. And then the intersection is just their overlap now. This guy. And then the last one, what is things that are in S but not in T? It's going to be that guy. Is that right? No, that's not right. I have to draw another diagram. Don't just make stuff up. You can leave that in. What did I do? Now I want S, so draw S. And I want things now that are, what is T complement? T complement is elements in S, not in T. So what were they? Oh, I did have it right, didn't I? No, because what are the things that they have in common, first of all? Those four guys. And then S was 1, 2, 3, 4, 5, 6, 7. So what is he? Yeah, no, because did you see the problem that I did? I switched it. And when I switched it pedantically, yep, 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 now we have to have T this. It has to be a subset to talk about the complement. And 11 was fucking with me because 11, because I changed the problem. But now you see how math works. You have to go back to the definition. T has to be a subset of S, and then I can talk about the T complement. So now that I have that, you can see now T is 2, 3, 5, 7, which is 1, 4, 6. Now this is the T complement. That was actually quite good. Also not planned, but this is how math works. You need to get dirty. You have to fall on your face a few times, get up, keep getting up, give me more. When you hit a brick wall, it's like eventually you bang your head, but I'm going to go get a sledgehammer. I'll see you in a second, wall. Next time what we're going to do is more of this, and then we'll get set builder notation, and then we'll start doing binary operations and relations and start tying together what the real numbers are. Patreon and shit.